guys, this is a new type of videos I was hoping to start producing since a long time ago. It was a big dream of me. Generally speaking, I have been experimenting with other kind of videos, you know, from my old retrotech videos. The first of a kind I started, but those took such a long time to produce, and I was so unmotivated to continue doing it. Then you have coding tutorial videos, but so unprepared, so unprofessional. They're much longer than I wish they have been. Opti of course, which is okay. I wish they were shorter too, and other Rant videos. And I'm trying to find the balance. I'm trying to find something that I'm very motivated to produce about ideas I want to get out, but somehow make it shorter, making the process easier. And this time I thought that it's possible to start a new kind of video. It's adjusted to coding, but it's more focusing, not explaining retrotech stuff, but explaining the insane ideas behind optimization, especially in retro platform. The thing is, there are very run-of-the-mill optimization techniques that I will try to explain those too. But I want to go beyond that, because you could be following the best standard rules of optimization, you know, write everything, you know, in assembly language, use fixed point, lookup tables, use shifts for bit shifts for multiplying and dividing by power of 2, unrolling parts of the code, cycle counting. You could be on some 8-bit computer on Amstrad CPC Spectrum. You can do all of that stuff for your amazing rotozoomer, and it would be like, oh, why is it still a single-digit frame rate? What else can I do? And then you watch another demo with the same effect, looking even better, even higher resolution, and running faster, and you're like, I went to the edge. How the heck did they pull that off? This is the thing I want to give you. This is the obsession, the passion, the when you have something, you have done everything, you have done all the tricks in the world for something, and it's like, that's it. Maybe there is something that can give me a 10% increase, and then you see something 300%, and you're like, how? See, you see my passion now. Now I'm more ranting here. So I really want to do this. I really want to do Optimosophy. That's why I call it Optimosophy, because this is more inspiring. And there are 3 categories of videos I have in my mind. In the first category, I will explain some of the tricks I already know and have worked with, starting with an effect in its original unoptimized form, like how you would write this effect without thinking of optimization, how you can make it work, and then gradually presenting improvements and measuring how much the performance has evolved from the first implementation. You know, and we could go, I could show you a run-of-the-mill tricks that will improve the speed, and then we will reach a limit, and then maybe I say, okay, now what do I do next? I've done everything. And then maybe I will throw some of the wild ideas that would suddenly break this gap and be like, oh, okay, that can go much faster than I would ever have thought with some out-of-the-box idea. And so in this category, I'll show things I already have implemented, and I will explain, I will put the knowledge out and the philosophy behind, and how I came towards that idea. In the second category of video, that might be more interesting, because I will be trying some new optimization I haven't tried before. I have lists, I have a lot of things, I'm doing a lot of coding, but there is a lot of list of things I would like to have done. There is a big list of, okay, I have a priority to finish some other thing I'm working now, but today I woke up and I thought some crazy thing that I must try, because it's insane. If it works, it's insane. If it works, it will make things much faster, and it will blow my mind, it will blow everyone's mind. and I have lists of absurd ideas, and sometimes those lists are in my mind. There is some old things I have forgotten, some old crazy idea I have forgotten. Maybe I have written somewhere, and then I lost my notes. But then it comes again, and I'm like, oh my god, I must try this. And these videos, they will be experimental, you know. They will be... I might even be trying things that will not work at the end. So you might see the failure of optimization. When you have some crazy idea, it ends up not being impractical, but making things slower than before for some reason. And I want to show this too. I want to show the failures too. I want to show the whole process, the whole philosophy. But the whole philosophy is that you have to try the absurd. You should not stick into programming dogma. Oh, don't even try this. It's a waste of time. It doesn't work for this and that reason. Don't dismiss the idea. Let's try and see what happens. Don't be afraid to try the most absurd ideas. This is the other Optimosophy philosophy. And in the third category, I guess I will maybe not work on specific idea, but discuss concepts of optimization. I mean, it's my whole ranting here, okay? The philosophical or ranting standpoint, common misconception and myth. When people say, "Oh, compilers optimize everything for you now. You don't need to do this or that anymore because now this is taken over," and then that's about assumption, as I said. I talked about assumptions. And there is other misconception. People say, okay, you will waste your time to optimize. Maybe you get a 20-30% at best, and then the hardware will be faster. But people think it's that you optimize and you get a 10-20%. There are some optimization, especially in retro demoscene coding. Some of them are a bit like cheating. Maybe they don't work scaled up in the practical, in the real world, but I will even show that, you know, the magic tricks behind that will give you like, okay, why is this running 500% now? How is it possible? I thought I could push myself to the edge and get a 10% optimization, 10% improvement, and you get hundreds of percent. How is this possible? I really want to blow people's mind and discuss the philosophies of optimization, ranting about them. Ranting about the absurdity of the ideas, but opening your minds, going against these assumptions, these programming dogmas, you know. So when you look at an old computer and you're like, oh my god, this is so slow, what can you do with that? Nothing. But then I show you how powerful the old computers are. What does it mean for modern computers? What does it mean when I code on a 4 MHz Z80 Amstrad CPC and then I go on the 3DO with the ARM 12 MHz and then I used to do something for the 486 and then I optimized things for the 386, and the ideas, because the CPU was lower, I had to invent more and more stuff to make, you know, BAM mapping and fire effect and plasma and everything faster, and then I took them on a 386, which is slower than 486. So previously I was like, oh my god, 386 is too slow, and now I'm like, it's fast. A 386 is fast. People see, oh, this console has 200 MHz and 32 MB of RAM. Oh my god, that's so fucking slow. No, it's a beast. A Nintendo 64 is a beast. It's a fucking beast. Okay, sorry, I'm ranting. No, but this will be Optimosophy now. It's funny, because I wrote a script now, and this is not written in the script. I started, and I guess I will do it like that. There will be always a ranting section, maybe smaller sometimes, and then I'll move explaining the main thing. And for this video now, I will not, because it's an introduction video, I will just take a basic effect. I will choose a platform. I will choose a 386 DX PC, but I will try on DOSBox now. And I will start with a very unoptimized effect and show you for this one I'm going to show you the run-of-the-mill optimizations only. I'm not going to show you any wild ideas out of the box, so that you get familiarized with the basic ideas, because we are going to use them a lot, and then when we hit the edge, then we will expand our brain. Okay. So I guess this one will be an introductory to see how it works as a format, this kind of videos. And I will choose a lot of platforms. Some of ideas I will show them on retro 8-bit computers, on others on later 32-bit machines. It could be an effect code on DOS, on 3DO, on Acorn Archimedes, and maybe I'll do some absurd experiments in modern PCs, like what would happen in a modern compiler if I do some unorthodox unrolling and they say the compiler does the unrolling for you, but or if I make an extreme unrolling for 1,000,000 pixels that will make the compiler exploded and I will destroy the cache. Like if you did the crazy stuff that they do in the retro demos in a modern PC, that's also a kind of experiment I would do. And some of them might even fail. We might try stuff and see, so that we explore things, so that we don't dismiss things and say that doesn't work and it's not a good professional practice and all that stuff. Anyway, so I will finish this rant and start. I think I will try to do less with animation and more with schematics or showing short parts of videos. I'm trying to find a way so that I will be able to produce this video without having to program extreme amounts of animation, like in my retrotech videos, the 3DO videos I was explaining things about Doom. You know, I'm trying to find a way to, maybe with some static slides and showing a bit of code, but not showing the results of things I have programmed. So let's see. So in this introductory example, I'm using my DOS demo framework, both for DJGPP and Wacom, but we will compile with Wacom anyway. And where I set a basic VGA 320 by 200 mode, and I was going to write the slowest plasma ever. I have some functions to create some palette in 256 color, and so if you were to write a plasma effect naively, it just adds sines and cosines, or just sines, it doesn't matter, together to produce the color for every pixel. So you would use math and floating point numbers and then convert on integers. But of course, if you do it like that, and here is where I'm using DOSBox, if you do it like that, it's very slow, of course, because I'm emulating, I think I'm emulating this one, 386DX33. So I'm going to put fast forward and then remove the fast forward. And I think I am on that one. I don't see the mark. So if you're going to do your plasma like this, and nobody ever does that, especially in old school computers, doing floating point and sines per pixel, you're going to get something like that. You're going to get a slideshow. Even if you set the CPU speed to the fastest Pentium 3 860 MHz, and DOSBox is not very accurate, so we must not care much about that. You will see the very slow plasma for using sines and cosines per pixel. Okay, 11 frames per second. And 3 point frame because I started slow. Let's put it back. So let's improve it a bit, still in a naive way. For the first attempt, we are going to create some lookup tables. I already created them. Some parts of the code to simplify the video I will have programmed more and just show you the evolution of it. I will not fully program real time in these videos. So I have already created 3 lookup tables, fscene1, 2, and 3. I put the arbitrary number, I make the table big, even though there could be a problem. And I used to call them fscene1. It sounds like it's float sign one, but I used to use the F for fake sign. That's another thing. Sometimes I use I sign for integer sign, but we will talk. Now the lookup tables are still float. I just wanted to show you that someone will create lookup tables to avoid the trigonometric sign, which are slow. And but of course floats are still slow, but we will see the improvement. And I still have the old code here. You see, I took this one and pasted it here, and I have a loop from 0 to sin num, and I cast the I to float, of course, and save it as a float. Actually, sines are double, but whatever. Now here I have psi plus tix. Tix is the time I get, and he plus psi. But here I do it for I, so I'm doing a generic sine table. So now I can come here and say fsin1 for x, no multiplies, no divides, fsin2. Now it will be for psi plus tix. No need to cast since the index is integer. No need to multiply, it's up on the lookup table. Fsin3 x plus y. Yeah, and at the end we still need to cast to u int 8. Says our color 256 8-bit color. And now this is a bad example maybe because the signed tables go from 0 to 4096, but this ticks will be increasing, so this can go out of bounds. So in the future you could do some modulo, but you have to see the when the sign repeats and do it exactly. But now for the purpose of our optimization example, we are going to 6075. This is a 386DX if DOSBox is accurate enough. So is there some improvement? Oh, whoa, why? Okay, something went wrong. And it's still not very improved. What the heck? Okay, got it. So, correction. It happened that I was doing... Okay, I was doing that. Okay. And because normally you have to make your signs to loop. And ticks, I forgot, ticks is coming from the system timer, and since I'm running DOSBox for a long time, ticks is in a very high number. Every time I run the program, it doesn't start from 0, it starts for something much bigger. So now this is not correct, but for now, for the purpose of the video, we will end. This is a power of 2 and you can do that. I will explain it in the future. And just to make it loop so that C plus tix is inside the limits of this table. It was outside of the table. That's why we got junk. And now I have to make sure 6000 cycles. This is a 386DX always. So now we use lookup tables while we are still using floats. We just avoid signs. And it is a bit, it's very slow. It's still a slideshow. But it is, if you combine it, it's faster than 1 point something frames. And maybe if you selected the fastest machine here, you will see it running, still slow. Is this 80 frames per second? Ah, it seems slow. Oh, the timer is slow. I know. Let me do that. We get the ticks here. Let's just do that. Let's make the ticks a bit faster for our purpose. Because it's 80 frames, but it doesn't... Okay, the ticks is not the best. It's a low resolution timer. I guess we can change that. We can say, okay, I guess I should have noticed that. But this is not relative to the timer. This ticks is a low resolution timer. Let's make this little change. What the hell. And you might not even need to end. No, keep the end. Because it's 80 frames in this Pentium 3. It doesn't look smooth. Now it looks smooth. And of course, if you go for the 386 DX at 33, it's going to be the slow thing. I do that so that it's fast when we finally optimize it. This ticks timer is... There is a hardware address and it's... I don't remember. It's time frequency. .2 ticks per second. I might have a millisecond timer in the future. Anyway, so I'm coming back to this. I did a little change. Now those arrays are in, they are not floaters anymore, and I cast them. Now because the sign is multiplied by some big numbers, this is going to be from minus 45 to plus 45. You know, if you had something like this, it's going to be a problem because the sign will be from minus 1 to plus 1. So when casting to int, most of the values would be 0. But since we scale up the sign, we can easily cast it to int and have a good precision. And that's the only change. These are cast to int, and now here they are added, and everything is integer. At the end it's cast to uint, this is unsigned char really, uint 8. I have some type defs. Yeah, I need to make sure we know what we are talking. uchar, uint 8, ubyte. I use this for porting some other projects anyway. It's the unsigned char 8 bit. So, let's see the improvement. We used to be a slideshow. Now this is a 386, so if everything goes right, it's gonna be faster, but maybe not too fast. Okay, that's a bit better. That's much better. It stops being a bit of slideshow. It's 7 frames because it's still a 386. I have some other techniques to make it faster, but some of them I might present in my next video because they are part of another set of tricks. But we will still try to optimize this. So from 1 frame it went to 7 just by using lookup tables. I might show you little things now. First of all, another technique. I'm showing you some run of the mill of the... Now this is more optimized the end, but we might not need it necessary. I might show you that if you have a number, a that increases, and it goes from 0 to plus whatever, 1, 2, 3, and so on. If you could do a modulo by 256, a division modulo, so that would go to 0 to 255. Maybe you do a modulo with 200, so it looks like that. But if the number is a power of 2, you don't need to do a modulo. You can do end power of 2 minus 1. That's a thing you can do if your number is a power of 2, but with modulo, I want to see how much modulos are slower. I want to show you that if you do a modulo, I don't even know, maybe it affects. We had 7.26 frames, let's see. Just a little modulo. I just want to show you the negative effect. So that's another run-of-the-mill optimization to use an end instead of a modulo for power of 2 numbers. The frame rate is flickering. It's 4. Oh my god, just for a modulo, it went from 7 FPS to 4 FPS. Just for a modulo. So what if we didn't do the end? Let's see how things affect. Let's try a few things. Now, the main important optimization is done. I'm just going to see. We spare the end. The frame rate is flickering there. You barely see it, but you will see the result later. 7.8 from 7.1 to 7.86 almost. But we can put the modulo, or remove it. It's just an example. This is a big number. If you make a demo where this plasma runs for 10 seconds and you use this increase in frame number instead of the ticks number, you will be fine. So you can cheat, or you can make your science loop at the specific points. So the next thing, some other kind of micro optimizations. We have a double loop. Outside is around y coordinate, inside around x coordinate. We notice here that fsyn2 psi plus frame num. This array is using y only, fsyn y. So we could put it on the outside loop. Sometimes you can put things on the outside. Call it psi2. Okay. Put it here. Let's see. From 7.86. Actually, I'm not doing the modulo anymore. I could do it outside because it's in the outside loop, and the modulo, the end, it's an end, and end is faster. You could do even the modulo outside because it's in the outside loop. So we put it outside. .39 frames. Okay, that's a small improvement. Now, I'm going to try this. I used to just write int, but there is also constant. I remember I was reading a John Carmack tweet. He was saying he was a maniac about constness. If you can use const, use it. And I noticed in some cases, maybe it's not the case now. We're trying stuff. But I've learned to use it as much as I can. If I know that at this point this is constant, I calculate I'm going to use it the same. Sometimes it's good for the compiler. Sometimes the compiler understands that this could be it doesn't need to be retrieved. It could be put into a register and used in a register inside. It depends. Sometimes it doesn't happen. Sometimes it happens. So let's see. I'm curious. And I have noticed in some cases, just making something const suddenly improve. Little things like that. Still 9 frames. Yeah, it's a little thing. Maybe the compiler predicts it, but it's good sometimes to test that. It's good to not assume, yeah, compiler knows everything. So maybe it's the same. Now it says 9.43, it was 9.39. There are macro differences when you try things. If it's close enough, maybe it's an illusion that it has improved, but it's good to do it. Maybe it will show. I think it will. Look, I'm doing my loop and I take the width and the height from the screen struct. And what I usually do today, I didn't used to do that. It seems like an extra step. First in height. That's what I do. And I have noticed in some cases, simple things like that. You will think, hey, the compiler is clever, is going to use for the checks, is going to use the constant values. No, it might not. It might think while it is looping here, it might think, hey, maybe the width and height from the screen struct might have changes. So I have to read it for the loop. But if you do things const, I have noticed it in other examples. And there are these little things. That's another optimization, or micro optimization philosophy. Little things like that could you might be wasting performance for little things like that. It's still at 9. I thought it would, but whatever. I guess it is clever. But sometimes, and by the way, where's my make file? We do we have these flags for the optimization. I found them. I don't know if they are the faster. I know in the DJGPP I use O3, the best optimization. Maybe I could use O fast. Maybe it's the same. Actually, as an experiment, let's see. I don't know if it will build. Just curious. Although we will continue compiling with. Let's see what the DJGPP does. Maybe you don't need turbo. Maybe you need that. DJGPP is much slower. It's supposed to optimize more, but it's much slower. Much slower. That's a warning. I hope it doesn't. See math. Okay, cool. Go about to 386 dig. Yeah, I'm curious. Demo J is then. Oh, it's already faster. 11 frames. Maybe I can continue working with DJGPP, or maybe we'll go back to. Yeah, let's go back to because we were comparing this version. And yeah, the compiler can give you sometimes some better performance. I was expecting the const. And don't assume because I have seen other code. I have seen even modern code. I was writing something on Visual Studio, and just by putting the width and height as const, it goes faster. Now how the old compilers, I don't know. You would assume You have to try sometimes. But those are micro optimization. What else can we do? Now this one, f sin 3 x plus y. There is an x here, but that's I can do in pointer so that I don't do the x plus y. It's a small thing, but maybe it gives a bit of performance. In the f3 in pointer f sin 3, since the y is affected by the outside loop, so that takes you in the f sin 3 I in the y index, sorry, the f3. So we can say f3x now in the inner loop. Okay, I hope it's okay. Let's see if that has improvement. So you see that sometimes I'm trying things and things might not work as you think, or might not improve. Okay, there is some improvement with that. We get 10 frames per second. 10.46 from 9.46. Just with that one, because we don't have the addition here. Now, what else can we do for an elementary optimization? Because I have some tricks upon my sleeve that I'm going to show in the next video. Another category of optimization that are more tricky. But the best I could do now is to unroll. Usually after 8 times of unroll it matters less, so I'm going to increase width by 8. Now the width is 320 by 2, it's 320, divide by 8, it's in the realm, it's divided perfectly, so it's for the specific screen width it's fine. And so I'm going to do, yeah, we can even put it in one line. The cast might be unnecessary, but maybe the compiler will argue about. And so we will do some unrolling and see how much it affects. Now you can do x plus 1 plus 2 plus 3. And that should be right. So we unroll a few times. And if you are afraid that, you know, unrolling your code might hit the cache, 386 doesn't have internal cache, as far as I know. And you can try with small unrolls, it's okay. You can always try, don't assume, try. So let's see. Oh, just the unroll. I mean, the unrolling is the biggest thing, okay. 19 frames from 10, 19, almost 20, almost double, and it's even like this, it's much smoother. And that's the beginning of optimization. Because the trick I have for you for the next video is going to boost this very high. Wow. So I'll try some final thing. Sometimes when you enroll, no, sometimes you might need to see the generated assembly sometimes. It's not certain. Here we do x plus 1 plus 2 plus 3, but I wonder if we say int x6 equal x. I'm just trying something. If you could do the plus index, although the plus index might be better for an x86 indexed mode, and it might not be better, but let's try. Let's try a few things, and then we do. It could be slower, but it's always as I say. You don't need to do it here. Instead of putting the offset mode, which might be better actually. What I'm doing might be slower, but you have to test it. I'm getting the x and I'm increasing, so that don't add it there. You do have to test all assumptions sometimes. I mean, if you don't want to waste my time like I do with all these optimizations. I'm curious. See, yeah, it's much slower. 14, 13. Because the x86 might compile the other thing better. It has an indexed mode. And sometimes, in some machines, maybe the other method is better, sometimes this method is better. You have to search for it. I guess this is the final form. So I thought, let's make a DJGPP version just to compare. The Whatcom version, I don't have it. Let's make the Whatcom version. Again, I cleaned up a bit. It's taking time with this. Maybe I have to do a fast forward. So for one final moment, the Whatcom version is doing 19 frames. The DJGPP version, okay, I might have changed. I didn't delete the other object files. Yeah. So is this in CVP? Okay, hold on. You've seen it already. I think something happened and and now make the DJGPP. Okay, now it combines. Something happened and normally it would, if you change something, it will recompile it, but now I had to clean it. I need to fix this warning. I don't remember, it's the same framework and I don't remember having that before. Okay, I guess I will remove my definition of P. Okay, let's see. From 19. Oh, what? See, that's weird. 12 frames. Are you... No, hold on a bit. Okay, and to finish my video, but you have to see this. This is related with other things I want to talk about in the future. Sometimes compilers, I fucking hate compilers. I should write everything in assembly. So, for some reason, previously, and it's harder to compile with DJGPP. It takes so much time, and for some reason now, I don't think it was like that. You have to delete the object file. This one with the 8 unrolls, it was like that. This will make, not this, in Wacom, it would make 19 frames per second. It did JGBP, that is supposed to be more optimizing compiler. It was making 11 frames per second. Then, as a test, I removed one line for some reason, and then, okay, the graphics were scrambled, it wasn't correct, but then DJGPP did 22 frames per second and Wacom did 20 frames per second. The DJGPP, so it might have to do with the size of the code. Maybe it does something, some crazy thing, maybe. And I know what they say. You know, the compilers unroll the code for your own sake or something. And there's the other thing, of course, that this is DOSBox and you don't know if it's the same on the real thing. So I noticed that. So I say, you know what? I will reduce my unroll codes. I'll do 4 times. Okay. I already compiled that stuff, and now this is the Wacom version. Now it used to make 19 frames per second. Now it dropped a bit, it does 17 frames per second. Okay, now this is the DJ GPP. Just for one line, it might be the fact that something goes over a size limit and the optimizer does something different. So with 8 unrolls, DJ GPP just failed from 20 frames per second, man, to 11. This is weird. So much that I could just do that. Let's try this. Who knows what it's doing? Let's try. This is the last one. I have to finish this video. It might have taken longer, but no, in the case of the DJ GPP, I need to delete all the object file for some reason. I need to check my make file later. Yeah, I'm curious. So both versions will not unroll. Let's see unrolling how well it did with the Wacom version and the DJ GPP. 8 times. Who knows what it does? Oh, am I? Okay, I'm full here. Can I go faster? But remember to put in the 386. Now, the what conversion? No unrolling. No unrolling 10 frames. The DJGP version, no unrolling. And it does the 11. That's the same number we did when we unrolled. Well, but when we rolled 8 times. If you unroll 7 times or less. But we unroll 4 times because it fits power of 2. Okay, this is weird, man. So the best version for both systems. This is better for DJGPP, but this will give edge to the watt conversion and somehow will screw the DJGPP version. And now for first part of micro optimizations, integer sign arrays and unrolling and moving some stuff outside. We have something that in Wacom it's for a 386 it's smooth for a beginning, but it can go better. We might be able to catch 60 or 80 frames per second. Also, this is not representative of how it would be on a real PC because of the VGA bottleneck. And I don't know if DOSBox emulate it, maybe not. And the thing is, this screen data pointer, it happens to be, I don't have it here. It happens to be the A00 in our case, the way I have programmed it. I have another mode where you could use a back buffer, and then the back buffer would be copied to the VGA. And that would be, it might be faster if you work byte by byte, but then it might be slower to copy the buffer. But anyway, we are just writing directly to the VGA. Anyway, this was the first Optimosophy video. It might be longer than I thought, but it's still made in parts, not entirely coding everything. So I stopped the recording, and anyway, it's time to stop and see you on the next episode. Bye!